Okay, so here a short view on the frame methodology. On the one hand, we have the practical works on reference brines. On the other hand, we have literature review. I did it in a kind of three-step, like one systematic review with keywords and sorting all this out. Then technologies review. I just introduced the most relevant technologies and try to collect a lot of characteristic figures. And then market evaluation. Yeah, this is in the end, the main challenge is market evaluation for the recycled salts and the quality requirements. Yeah, finally, I try to put this in a synthesis, create generalized criteria, application on the practical, on the reference brines, and finally there's the conclusion. So let's have a short view on the literature results. One researcher who published a lot in this field of ZLD and techno-economic evaluations of these processes is Panagopoulos, and he proposed to structure these processes in four parts: pre-treatment, pre-concentration, like with reverse osmosis, evaporation, so the thermal evaporation part or thermal concentration part, and crystallization. The key topics that are reported, on the one hand, removal of refractory organics, removal of hardening agents. These can all be, let's say, referred to the pre-treatment. Also like the removal of silicates. Yeah, they all are normally, let's say, targeted or addressed in the pre-treatment to enhance the yield of the following process steps. So then there's the topic of non-selective concentration, so water recovering, brine concentration. It's the question of energy efficiency. I think you can imagine RO is more efficient than thermal evaporation, and to try to make all this more energy efficient without changing the chemistry in the end. Then there's selective concentration. There are developments in the field, for example, of nanofiltration or electrodialysis, metathesis, so processes that are used to concentrate our brine and also, like in the same process, make a fractionation, yeah, generate at least two output streams with different stream compositions. Of course, crystallization is in the focus, and energy recovery from brine. I put it in brackets here because it's like not directly linked with my topic, but it's also, let's say, frequently reported in the publication. Yeah, the amount of technologies or the tree of technologies that are covered in the publications is really big, but a lot of them are, let's say, in lab scale, maturity grade, and also they are, let's say, trying to cover a really specific problem. I highlighted in pink. I highlighted the ones that I chose for my thesis to be relevant because of its technological maturity, because there are industrial near characteristic figures available. Okay, so that it's possible to create process out of these with, let's say, industrial near characteristics. And so the most important that are in the end part of my later process proposals are chemical precipitation, nanofiltration, reverse osmosis, the thermal classics like brine concentration, brine crystallization, and ion exchange, which can play a really big role in the pre-treatment for removal of hardness formers and also resalting, like, let's say, trying to sort the ions to create marketable salt products later. Okay, coming to the practical methodology. We worked a lot in the lab scale, in, let's say, iteration with Freak simulation. Freak is an open source hydrogeochemical simulation software. You can simulate, for example, steady state equilibria for for solid liquid, for liquid gas, and for all these speciation reactions that are needed. It comes with a lot of, let's say, data set, a big data set, but also it had to be enhanced a little bit, but it's all open, so it can be manually enhanced with as and when the thermodynamic data is available. Yes, based on the steady state simulations, I did some process design and balancing, yeah, and then this was upscaled and finally economically evaluated. Yeah, some words about the economical evaluation. I think the best, or in my case, I found the best way would be to levelize all cost to the feed. I call this levelized cost of treatment. Yeah, maybe, yeah, you can imagine a brine treatment process has different functions. It can, on the one hand, it can reduce the brine. On the other hand, it can produce water. And so if you also consider salt recovery, it also can produce salts. Yeah, so to consider all this, I thought the best way is like to normalize this all to the feed flow and call this levelized cost of treatment. Yeah, we have the invest and operational cost, CAPEX, OPEX, disposal cost. Yeah, so you also have to consider what are the residues and effluents that have to be disposed of your process, and all, let's say, relate this to the feed volume flow. Yeah, in the next step, you can also consider the substitution with revenues from, let's say, recycled water or recycled salts. Also normalize this to the feed, and you get some LCOT sub. I call this subsidized levelized cost of treatment. Yeah. Oh, my screen is getting black here. I don't know. Ah, it's back. Okay. Yeah. To calculate the capex, I used the capacity model in this form. You have some constants and scale all this via capacity. So you have a steady curve of investment costs. So this can be able to, let's say, calculate a lot of different variants in quick time instead of, let's say, making one specialized design, make a price, a bidding, whatever, and then you get one result, and you have to repeat this a lot. So the capacity factor or the capacity model was the correct method in this case. Yeah, salt price on the market, you see they are, let's say they have a bright or a wide variance, of course, depending on quality and local availability. Yeah, not on every market, at least if there are different continents, of course, they have different natural resources, and some have to import, some have to synthesize salts. Yes, these have a lot of variation. On the other hand, we made, let's say, qualitative review of the disposal costs, which is shown here. And it figured, or it showed out that the disposal cost can be, let's say, clustered in two dimensions. On the one axis, you can have the salt content. On the other hand, the organics content. Yeah, just qualitative review. So if both is low concentrated, at least in Europe, standard disposal way would be like indirect discharge, maybe in a few cases also direct discharge. So in the local sewage system or natural system, yeah, of course, this is only allowed when the concentration is really low. If the salt content gets higher and higher, this is, let's say, solid waste for disposal. You have to transport it to a safe site, and then that is normally stored in tanks. This is really expensive. Yeah. If you go on with your concentration, you will somehow, at one step, you will cross the solid liquid line, and you will have a solid residue. And there we see two possible ways. So one is the solid disposal on a, let's say, disposal side, of course. And We have another one, mine backfilling, at least in Germany and some European countries, this is an option. Like if it's storage stable, low organics, then it can be put just in old mines to make it stable again. And yeah, we also can call this utilization officially. Yeah, and this is the most, let's say, cheap solid disposal way. And in the end, in my process, this was always like the target disposal way. Okay, so now we have reached the results section. Yeah, just a short overview of the two, let's say, major effluents. One is from a coffee industry. It's just, in the end, it's just an industrial coffee brewery, and they produce a lot of brine with refractory organics and salts, of course, mainly from the cleaning process. And the other one is from the cosmetics industry. Maybe some of you know L'Oreal. They were part of the project with one reference site. Yeah, and I just tried to highlight the most interesting, let's say, parameters. One is so the volume flow, daily volume flow, cubic meters per day. So the coffee production, it's in Berlin, it has a volume or effluent mass volume flow of 1,100 cubic meters per day. In contrast, the cosmetics, it has 66 cubic meters per day. The next one is TOC, total organic carbon. Let's say both in a range of 300 milligram per liter. TIC, inorganic carbon or carbonates, let's say 140 to up to 200 milligram per liter. And the rest main, let's say, components are sodium chloride in both cases. Yeah, all the others have no, let's say, special meaning for now. So let's say mainly it's sodium chloride, and yeah, here you see a big difference. Like the effluent from the cosmetics industry has in a range of thousands milligrams, so gram per liter, while the other one is let's say milligram per liter. So let's look on the process proposal we developed in course of the HyCon project. After an RO to generate first concentrate, we put in an F. It had the function to remove the main or reject the main organics, TOC, and a lot of these multivalent and hardness formers, and they were put to a MEH multi-effect humidification. Don't have to go into the details. It was just a non-selective evaporation. So we produced one solid waste stream out of this NF concentrate. The permeate was further, let's say, concentrated, and then we had a second evaporation, and this is a fractional evaporation where we get two solid outputs. One is single salt or our target salt, which was intended for reuse. For the coffee industry, it was sodium carbonates because of the better TIC Na plus ratio, and for the cosmetics industry, it was sodium chlorides. And here also we have another solid fraction. I call this mixed salts, but without organics, which was intended to be used for mine backfilling. Yeah, so some kind of cheap disposal method. And of course, yes, not to forget all the water coming from RO and the evaporation processes for water recycling. So now let's look at the costs of all of this process. We have for the coffee industry here, starting with CAPEX and OPEX, roughly about $2 per cubic meter. They are both at the same level. 60 cents per cubic meters disposal costs all for the whole process. I would say I can consider this as low in comparison to the other ones. And then we have $2.20 per cubic meter green box. This is our revenues from our recycled water. This is big. And then now we have 3 cents per cubic meter, so nearly nothing revenues from salt recycling. Yeah, this is really low at the first hand. Of course, this is caused by, on the one hand, sodium chloride and sodium carbonate are, let's say, not highly market value salts. They have moderate market value. And on the other hand, the concentration is not really high in our feed flow. Yeah, so salt recovery is not that efficient in this case. So we end up in a, let's say, net treatment costs or levelized cost of treatment subsidized of $2.60 roughly about. This is in the same level as the current state. I just show here it's indirect discharge. Yeah, it's the same amount now. Just for comparison, I calculated a conventional non-selective ZLD without salt recovery process. Yeah, we see CAPEX, OPEX are cheaper. I think it's clear you have less technology or less complicated setup. You have a little higher disposal costs. You have the same, let's say, revenue from water recycling. The impact of salt recycling is nearly zero. And so finally, you have roughly $1.90 per cubic meter cost for ZLD process. So this would be even better than the current indirect discharge. Yeah, so in the end, selective salt recovery, this can be stated here. It drives the CAPEX, it can drive the OPEX, it reduces disposal cost, and water recovery in comparison to ZLD is nearly the same. For the cosmetics reference, let's say qualitatively it's the same. The figures on the other hand are on another level. Especially the CAPEX and OPEX are on a much higher level. I thought, why could this be? This is because of the much lower volume flow. Much lower volume flow makes every treatment cost specifically higher. CAPEX, OPEX, I think it's clear. So in the end, you end up in both process combinations. The complicated HYCON process, the standard ZLD process, you end up in costs. Here it's nearly $11 per cubic meters. Here it's $5 per cubic meters. This is much higher than the current or state of the art or current solution. They have an RO and indirect disposal of the brine of the RO. Okay, coming to another, let's say, reference brine. Here, this is a satellite picture. It's a Jordan Eschidia mine, Jordan phosphate production. Here you see let's say the phosphate rock is scratched from the surface, manually pre-processed, and then in the end the production, this is here the production side, is like they put just a lot of sulfuric acid and dissolve all this stone or natural material. Then in the first step the phosphogypsum is produced, and then the result is some kind of phosphoric acid with some all of the natural residues from the natural stone inside, staying inside solution. So let's say it's a phosphoric acid production in the end. From this, finally, a lot of, let's say, different products are generated, and the wastewater looks like this. It has some kind of moderate volume flow, around 500 cubic meters per day. Really low pH. I think it's clear from the production. And then it has, let's say, 33,000 milligrams, so 33 grams per liter phosphate, 15 or more than 15 grams per liter fluor or fluorine, and both in a range of 5 grams per liter sulfate and silicium. So it's like in concentration, it's a factor of 10 higher than the, let's say, first presented references. Yeah, so the process we developed here is looks like this. At first, we took the cheapest neutralization agent, NaOH, sodium hydroxide, and two-stage neutralization because in different pH ranges, different, let's say, salts precipitate in these steps. The first one is sodium silicofluoride, Na2SiF6 or maladrite, the hydride name. This is has a quite good market value, so this can be used for, let's say, reuse. And in the second stage, there's a mixed salts, nearly, yeah, all this calcium phosphate, magnesium phosphate, but all in low concentrations and all mixed with nearly no market value, I think. The nice aspect of this is, like, let's say, the effluent of this neutralization is nearly depleted of all these hardness formers and of silicates. So it's perfectly prepared to put on a conventional seawater RO. There we have the first water recycling step. And we can think this process to the end, put all this in another evaporation, crystallization, and there we could, let's say, separate sodium phosphate as salts for reuse and have a minimized liquid effluent. So this is process we call a minimum liquid discharge. So if we look at the cost balance here, we see capex, okay, it's moderate, lower than $3 per cubic meters. OPEX are really high. Why are they high? On the one hand, of course, there's the energy input for the RO and evaporation, crystallization, but the biggest share is the chemical input of the sodium hydroxide. Disposal costs are low, water costs are, let's say, moderate, but here we see a big green, let's say, negative costs. These are the benefit from our salt. These are recycled from the process. Yeah, so let's say the maladrite and the sodium phosphates, these are, let's say, valuable salts. So all this ends up in a negative cost balance, so we even get money for treating this effluent, theoretically. Sorry. I just added up here, like always, the status quo is, let's say, they are taking this, doing it in evaporation ponds or putting it in evaporation ponds, which can be, let's say, nearly $3, a little bit more per cubic meters costs in this case. Okay, last case study which I want to introduce is so also from mining industry. It's a potash fertilizer production located near the Dead Sea. Here we see the south end of the Dead Sea, and there are evaporation ponds. And after being, let's say, pre-concentrated in these evaporation ponds, there's a production where they, let's say, have different evaporation and redissolution steps and generate potassium, mainly potassium rich fractions for fertilizer purpose. Yeah, and the effluent is then put back into the Dead Sea. Yeah, it looks, we got a sample, it looks, let's say, like this. Yeah, you can even see it with your eyes. It has a really high amount of solids inside. You can see how this has settled down. So it's, let's say, not saturated, but it's oversaturated with salts. Yeah, so on the left hand, I show the analyzed parameters. On the one hand, the volumetric flows are really, let's say, extreme. I just have a reference for calculation. I just took 100 cubic meters per hour, ending up in 2,400 per day, but these are in the end much higher. But we just need some figure to start with calculation, so I chose this one. And then I show the main ion composition of the liquid and the solid phases. It's like liquid phase mainly is chlorides and magnesium, and the solid phase is mainly chloride, magnesium, sodium, and potassium. Yeah, it's interesting that they are so different, but it's also helpful. We can consider the solid phase as a mixture of halide, so the natural, so sodium chloride salt, and carnalide. This is a potassium magnesium chloride double salt. Our process proposal finally was like this. First, put it to a SL separation to reject all the solid phase. You get some halide and carnalide mixed with, I think in this mix it will not have some really market value. You can, if it's let's say, maybe it's possible to put it back in one of these evaporation ponds upstream, but on the liquid phase is nearly, let's say, or highly pure magnesium chloride, and in a evaporation crystallization we target to create magnesium chloride salts of it. Yeah, like here in this phase or in this example, bischofit is magnesium chloride, I think the 6-hexahydrate. This also takes with it a lot of crystal water. This was our project proposal or process proposal. So when looking at the cost setup of this process, also you see a really good, let's say, balance. Yeah, because of the high concentration and market value of the bischofit, you get a big, let's say, revenue from salt recovery in theory, and all this could support or subsidize your treatment, and you, in the end, you end up with negative treatment costs. Also here, status quo, Dead Sea disposal with 30 cents per cubic meters is really cheap. Yes. Okay. So these were the, let's say, case studies. Now let's look at what are the general or the generalized criteria to create a process. Of course, I think the most, the one with the most impact may be the profitability criterion. Yes, if you get some revenue or if it makes sense. A researcher named Shah Mansouri, he did some, let's say, simplified proposal for a formula, and I took this one and made it a little bit, let's say, more detailed, because I think he left out some interesting impacts. Yeah, but the idea, I think it's quite easy. Yeah, so the economical potential that comes into your system is like the revenue from the salts. This is set up by the salt price multiplied with the concentration and the feed flow. So salt price multiplied with salt mass flow is like, let's say, your maximum you can get out of your salt that you want to recover. And on the other hand, you have the costs. These are the disposal costs, the operational costs, and the operative costs. And if we want to think about, is it, let's say, makes it sense to recover a salt or not, we have to look at delta costs. Yeah, delta disposal costs. Yeah, if we recover a salt, we don't have to dispose the same amount. Yeah, if this difference is lower than 0, then we have a positive business case in theory. I think it's clear, and the nice is you can plot this on a diagram for salt, for example. On the x-axis we can plot the concentration of a salt, and on the y-axis the price of a salt, and then just create break-even lines for a certain process combination. Yeah, just here one example: nanofiltration plus RO plus brine crystal, brine concentrator, and then you get some break-even points, and then you can just read from this chart. Yeah, everything that is on the right-hand side, right top side, is in profitable area. On the left side, in the not profitable area. Yeah. So, for example, if you have a salt with, let's say, 10,000 ppm concentration in your feed, and it has a market value of $500 per ton, you end up in the profitability area. If the salt only has a value of $10 per ton, you are not in the profitable area. I think it's quite easy to read. So it's helpful to get a fast decision. Also, you can see here the influence of the volume flow. It's the same plant configuration for different volume flows. So the higher the volume flow, the bigger is the profitability area. I think it's also quite clear. Yeah, but there you find a little bit the, let's say, link to our case studies. High volume flow is good. Okay, so of course, next to economical criteria, we have to check technical criteria. And from my literature research, I set up the basic ones, like, for example, hardness has a limit for treatment with RO. Organics has a certain limit, whatever. Yeah, based on the literature results, I would say it's at least possible to create some characteristic figures that can be set up here as limits that are typically valid. And so if you put all this together, the economic criteria and the technical criteria, then with some logical, let's say, operators, you get some logical charts like this. And in the end, you get a decision, what's the correct technology to treat your sample. Here, this is the example for pre-treatment, and the question, is it meaningful to treat your, let's say, to apply an ion exchanger or nanofiltration, or what's also possible that none of these is a good version. This is the outcome of one of these logical charts. Looks a little bit like a software. Yeah, another thing, I think I have to develop some kind of workflow, how to, let's say, apply all these functional or logical plans step by step to create a process. And this is, I created some kind of algorithmic workflow. Also looks a little bit like this chart from a PC program, where you can just step by step see, okay, I have to check this, I have to check this, and I have to check this. We'll see it in the next steps how to apply this best. The target was to generate repeatable results. So if you start with the same amount of information, that you always get the same result. And on the other hand, I wanted to have this a little bit ready for automation, because this is the next step, I want to do this or implement this as a software. The version that is now, let's say, or the most recent version always creates ZLD process. So a process this has no liquid effluent left. So it's repeated till no liquid effluent is left in your system. Okay, so let's apply this on our reference cases, and then we are finally done. Take a look back at our coffee production wastewater, and here I have a plot of the profitability chart, concentration, and the price, and there you can just plot all possible salts which can be formed according to your feed stream analysis. Yeah? And we see the break-even curves for two processes, for nanofiltration and for ion exchanger. And we don't have to read all these. There are a lot of salts that can be formed. We don't have to read all of these. The important thing is that we know we have few of these are in our profitability area, which is on the right top of our charts. It's sodium carbonates and potassium carbonates, for example. Yes, and in this case, I have another fraction. I call this mixed. This is let's say, mixed fraction, which is, let's say, mainly depleted from organic components that can be utilized as for mine backfilling. Yeah? Why does this have a market value? You cannot sell it on the market, but in the end, if you don't have to dispose it as special waste, you save nearly $500 per ton for the salt, so this has an indirect market value on this hand. Okay, yeah, for our looking in our, let's say, logical plan, we have the profitability criteria for ion exchange and for nanofiltration. These are true, and we have a yes here. Yeah, on the other hand, okay, we see, okay, both of these technologies make economical sense, but on the other hand, we have to step by step check the technical criteria. On the one hand, this is hardness is higher than the limit, organics is higher than the limit, and step by step, we can fill out all our criteria and get, say, technology proposal for our first treatment step. Yeah, so the first treatment step for our coffee production wastewater is defined, nanofiltration. This, in the end, generates a permeate and a concentrate stream. And so what to do now? We just do the same checks again for each stream and each stream as it's described in our workflow till we get a full process proposal. The automatically generated proposal looks like this. We have one feed. We have, of course, we have, let's say, neglected all these water streams for recycling because these are, let's say, for simplification of the display. So we have only two residue streams, the mixed salts for mine backfilling with low organics, and another stream, mixed salts with organics. Yeah, these are generated in the end by the NF and then concentrated till the end. Yes, I also, let's say, put the 4 phases of our ZLD processes: pre-treatment and F, pre-concentration, RO, evaporation and concentration here. So you can see the 4 phases again. Yeah, so now the interesting question is, okay, this was, let's say, some kind of automatically or semi-automatically generated from our abstract criteria. How does the cost chart look like? It's here on the left hand. I just call it new process, and we look CAPEX, OPEX are quite low. Water recovery or revenue from water recovery is the same as always, like $2.2 per cubic meter. Zero benefits from salt recycling, but we get net costs of $1.08 per cubic meter. This is even better than the HICON process, which was individually developed, and better than the ZLD process, and better than the indirect discharge. So, of course, the question is now, why is this process better than a conventional ZLD? It's because the NF, let's say, the NF removes all the hardness formers or a big share of hardness formers and a big share of organic carbon or organic matter, so that the permeate can be put to an RO, which is much more efficient with respect to invest costs, also to energy, than this crystallization. And so this process is more economically meaningful than a non-selective ZLD. Okay, I think in my work I checked, of course, all the other references, but with a view on the time, I put all this in the backup and would proceed to the conclusion now. Yeah, we have, I divided the conclusion into 2 phases, like one focused on the thesis and one on the outlook of salt recycling in general. Okay, we look on the core topic. I would say, okay, the relevant process steps could be defined, and application criteria and workflow was, let's say, developed to generate some kind of automatic process proposal, and this was validated, and the results are at least competitive to, let's say, processes that were designed individually. So I would say it's some kind of proof of concept is there. Of course, there's what always stays open in some kind of generalized approach is project-specific optimization. For example, you could put some HPRO to make further energy optimization, or use, let's say, internal recycling salt streams for internal ion exchange regeneration. This all is not yet covered now and has to be covered individually. Also, the big topic of, let's say, from calculation salt to salt product, you need to consider post-treatment, like drying, like maybe enabling certain granularization or let's say crystal size, and all these quality certifications, whatever. Yeah, this is not yet covered in this generalized approach. Yeah, I just put a certain fixed amount of extra money to cover all this, but of course this has to be clarified project specific. Also, like soft criteria, for example, some enterprise regulations, whatever. This cannot be covered systematically. Yes, with view on salt recycling as a topic, it stays, let's say, a little bit challenging. I think it could be seen that the profitability area of all this, if you have, let's say, a kind of realistic concentration, the profitability area is always quite low. So you need really a high concentration and a high, let's say, market price of salts to make salt recycling really, let's say, economic. On the other hand, there's still open the questions of legalization and also acceptance for recycling products. If it's written recycled from wastewater, I think everybody can imagine that it's a little bit difficult to get acceptance for this. Yeah, so for short-term perspective, I would say, okay, yeah, it's a little bit reserved. Okay, but it's not excluded. Yeah, I would say let's focus on the projects that have good chance for really realization, and these are all these, or the favorable conditions for project realization is like maybe salts are critical resources, for example, lithium or some local, let's say, critical resources. I think what is beneficial could be like internal reuse options. So, for example, in the same production site or the same company or the same chemical park, if you find somebody for internal reuse, then I think you can bypass, of course, some of these organizational limits. Yes. Long-term perspective, as I just linking to the introduction, the situation, the ZLD market is growing, and the question of what to do with our solid waste will also, let's say, push the need for salt recycling from this side of view. So I'm optimistic that yes, the conditions will get better in the future. Okay, yeah, outlook, just to the core topic, as I told, or as I said before, I would like to implement this as a software. I think the concept is prepared, just do it now. And yeah, I'd like to implement this and apply this to a lot of special cases just for iterative improvement. Yeah, I also found out that there are some pre-treatment options that should be implemented to cover a broad, more wide range. It's like erosion for dehardening, ion exchange, different resins, and silicates treatment, of course, is a important aspect that is now, let's say, not yet 100% covered. Also, with my work on the reference cases, I thought that MLD process or a criteria to define if MLD makes sense or not should be helpful. And at first, it was like, let's say, a niche application, but I found out, especially in water-stressed countries, MLD, if there's a possibility, for example, for evaporation ponds, whatever, it's also a really valid option. And the implementation of lithium, of course, yes, I don't have to talk about, I think, much. Okay, yeah, and I hope that this method helps to, let's say, push projects, push reference applications, and then, establish salt recycling till it's established as paper or glass recycling now. Okay, thank you. For your audience. And yes, I'm open to questions. And if there are questions in your letters, I hope that Masoud would maybe help me with the translation.
Thank you so much for very informative presentation. It really was impressive. Since there was some issue, there was some waves of, for example, saying that zero liquid discharge is the best option, like zero waste, everything that becomes common in popular, and the experts search for it and follow it. But the critical point is to define the cost-effective solution, as you presented very effectively. The most interesting points that I learned from your presentation was that the curve, the lines that you presented, the profitable area, which is the high concentration, should comes with the high price value, and it's very important. There are some questions that first, I think most of there are students and some of experts in Iran. Some ask about your presentation. If available, you can hand out in, for example, PDF format. But also I have recorded your presentation, and everybody who wants to access the presentation can have the access via the links, the similar link that you joined to the session. So the presentation can be accessed through the films of recorded, and you can have all the materials if you want to review that. Also, if دوستان اگر سوالی هست و مطلبی هست میتونن در واقع مطرح کنن که آقای دکتر هاگن اون رو پاسخ بدن. حالا اگر نیاز به ترجمه‌ای هم باشه، حالا از روی پرزنتیشن ها معلوم شد که در واقع ما توی صنایع مختلف چگونه میتونیم بهترین روش رو ارزیابی کنیم با تحلیل اقتصادی. حالا بحث این که چقدر اون نمک ارزش اقتصادی داره و چه غلظتی در اون پساب یا آب شورابه هست و به این شکل در واقع برآورد مناسبی میشه از بهترین راهکاری که برای اون هر صنعتی میشه ارائه داد. I gave some points in Persian for the audience, so
Okay,
Also,
can I answer just one to sharing the presentation?
yes, of course.
Okay, yes, I would love to share the presentation, but it's, let's say, it's before publication now, and I'm not sure. I have to check if it's so a problem, okay? But I
Yes.
can share it to you for, let's say, unofficial use. I can share it for now, and I will ask Sven just double check if there's an issue with using it, for example, before it's officially published, okay? Because sometimes
Okay, no
if
problem.
publishing, they ask if it's, yeah, so, okay? For internal use, I think no problem. I will send you the PDF soon.
Thank you. Yes, because there have been some real projects in, I think, in Jordan. Most of the projects were located in Jordan, and 4 different industry were compared in this presentation. So it's very critical to admit the confidentiality limitation for the projects and consider if there is any limitation to distribute the presentation. Of course, we understand your concerns, and I think the audience are very satisfied with their current presentation, I think. I have a question that about your cost calculation. Did you consider the capital recovery factor for the investment cost, your capital cost as your capex formula? Because you added capex to opex, yes, operational cost to capital cost. And I think they should be calculated based on annual, yes, per year. The cost annually. So you may have multiplied the capital recovery factor for the capital cost. Is that true?
Yes, that's true. Of course, CapEx are one point and OpEx are running costs, and you have to find the same time base. Yes, and I don't know from my mind. I think I used a real interest rate of, I'm not sure, 1-2%, and span, what's Abschreibungsdauer? A time frame of 7 years. Yes, of course. Yeah, this is in my written thesis. I always explicitly write all this down, and you can read the final values. Yes, but of course the interest rate is can change fast in these times. Yeah.
Okay. It was very interesting for a research thesis. I think the most useful point, the most critical points in the works I see in the Technical University of Berlin, the chair of environmental process engineering, there most of them are real projects, and most of them have economic evaluation, and the aim of the research is put the products into implementation, and it is not merely for theory or for thesis, and it's very important to put the science into real implementation for the industry, for the society, and for the environmental protection. So it's very precious for me and for the audience that you presented this subject. And I can have another question. In all these 4 industries, you worked and you tested on the real treatment plant or apparatus and you didn't have any, for example, pilot plant or lab scale tests. Is that true? As I understood.
Yeah, so in all cases, we worked with the original wastewater. So after pre-test, of course. Yeah. So in most cases, so normally we started to work with synthetic wastewater, but then when it was far enough, we got the real wastewater, and it was always like our aim to make the final validation with real wastewater. Yeah, in the HiCon project, which was, let's say, we had enough of time and budget, we set up like this plant, which I showed, RONFED, as a demonstration or demonstrator. This was really operated, and it was a lot of work to get this enough operational data. For the Jordanian samples, it was, let's say, without project work, okay? we just got the sample and worked on it, but we did not have the budget to set up a demonstration plant. But we hope to do this soon, yes, because it's like, this is also why I wanted to have Mohammed Aladous in my supervisor group, because he's our contact to Jordan, yes, and he organized also, let's say, the samples, and I hope that we can somehow use this connection to continue with implementation of these ideas.
Mm-hmm. That's okay. And the projects are or it has finished?
The project the project I was writing about are finished. Now, finally, I think the last one was the Weiss with steel industry, where Moritz is working on. Yes, but we all, let's say, we have in some other projects, which let's say the brine treatment is also bound in another project, and we typically are involved. For example, green practice, which is water from photovoltaic solar modules, solar panels productions. This will be, let's say, I will work on this after my holiday. It's also interesting. Yeah, it's they have acidic and alkalic two wastewater streams, and it's a little bit near to the phosphate industry wastewater, because they are also working a lot with fluoric acid on silicates, whatever. Yeah, so chemically it's a little bit linked to the phosphate wastewater, and we can, let's say, at least transfer some of our data. And yeah, and there's the fertilizers project, where we are covering lithium brines from Chile, from a Chilean brine lake, Salar da Atacama. I think it's the biggest natural brine lake with lithium worldwide, and we have a project with them. Also, we are trying.
Which country you said?
Salar Atacama. I can.
Is it located in the country? What country you said? What country?
Chile. Chile. I can write
Chile.
it in the chat.
It's very interesting. The largest lithium lake, yes?
Yes,
Okay.
yes. So I think it's in the profitability area. It's far above. Yeah,
of course.
yeah. But it's technically challenging to separate lithium and sodium, and yeah. However, we'll start also practical work by the end of summer.
Thank you so much. If there is no question, I thank you again for taking time, for preparing the very precious presentation for our audience, for our university colleagues, and for students that we are in IoT. Greatly appreciated, and hope success for your future projects. And I hope we can see you again in next maybe works, and you present us again in the future. Thank you so much.
Yes, I also hope so. And yeah, thank you for listening and yeah, sharing the ideas, hopefully, yes. And I will just send you the presentations. Please contact me if there are some questions. Bye-bye.
Thank you. Thank you so much. Thank you, everybody. I say goodbye to everybody, and thanks for their presence in the session, and I hope we can have the other session in future. Goodbye.